Hello everyone, my name is Arwa. This is a complimentary video to my capstone in computer science project where I break down the code for the Budgetier application. Today, I will be discussing the benefits of manually implementing a dot product similarity search in a retrieval augmented generation or RAG pipeline. Some dependencies required for this program are PyMongo, NumPy, and sentence transformers. This is the documentation for the installation and usage of the Hugging Face sentence transformers library. I used the all-mini LM L6 V2 model, exemplified in the documentation. This is the MongoDB documentation for Atlas Vector Search Quick Start in Python. It shows you how to declare an Atlas Vector Search with Python code, first you import your URI string, you declare client, you access the database and the collection, and here you create your index model. These are the fields for declaring an Atlas Vector Search. The type is vector. You create a path. It doesn't have to be plot embedding. It can be whatever you choose. The number of dimensions are the number of vector categories for whatever LLM model you choose. For this particular model, it is 1,536. For the model I will be using, it is 384. The similarity is dot product or cosine or Euclidean or whatever you choose. For this project, we will be using dot product. The quantization is scalar. I didn't declare using MongoDB code. I declared my vector search with Atlas, and so I'm going to show you how to do that. To create a vector search with the Atlas UI, navigate to the clusters page. Click on Browse Collections. Navigate to the collection you are creating a vector search for. We are using the transaction collection. Atlas Search, and click on Create Search Index. Here we want to create a vector search. The index name is Semantic Search. And the accounts database for the transaction collection. Okay, and now we click on JSON editor and we click next. Here I will copy and paste the fields parameters. The number of dimensions for the LLM I'm using for this program is 384. The path is description embedding or disk_embedding. We're using the dot product similarity search and the type is vector. We click next, create vector search, and we wait for it to be ready. The documentation for the sentence transformers and creating an Atlas vector search with Python code will be in the description below. Okay, let's jump into the code. First, I will show you how to set up environment variables. There are often many questions regarding this. In the .env file, write the variable name. The naming convention is all capital letters. An equal sign and the string assigned to the variable enclosed in single or double quotation marks. Then, in the file calling the .env file, import OS. Import load_.env from .env. Then call the load_.env function. To assign the abstracted .env variable to a declared variable in the calling file, use the os.getEnv function, passing the .env variable name to the function. I am retrieving my MongoDB URI from the .env file using the os.getEnv function. I am creating a client with PyMongo, and I'm accessing my accounts database and saving it to the DB variable. And I am accessing my transaction collection and saving it collection underscore T variable or call underscore T variable. Let me give a quick operational overview of the rag.py program. The program retrieves a user ID along with the declared query, brunch. Then it calls the process transaction embeddings function, passing the user ID. The function processes the transaction collection, iterating through all documents matching the past user ID with an existing description field. A sentence is created of each transaction's category and description. Then, an embedding is generated with the LLM and assigned to the description embedding field. The document is updated to contain the embedding and saved. After processing embeddings for the transaction collection, a similarity search can be conducted. An embedding of the query is generated, and the dot product between the query embedding and the embedding in each document in the transaction collection matching the user ID is calculated. The selected range of most similar results is then returned. In simple terms, this program uses the Hugging Face large language model to find the most similar transactions to a user's query using a dot product similarity search. Now we are going to test the generate embedding function, passing the user query brunch. In the generate embedding function, the query string is received as a sentence variable. A model is created using the sentence transformer framework, taking the all mini LM L6 v2 model string as a parameter. Then, the sentence is encoded using the model and assigned to the embeddings variable. After completion of this process, we are printing the shape of the embedding and the first 5 values to the console. The program then returns a list of embeddings to the calling function. Let's run this code. Here, we can see the embedding shape is a 1D array with a range of 384 features. And the first 5 embedded values demonstrate an array ranging from -1 to +1. Now, we will run the process transaction embeddings function to generate and update all transaction documents matching the user ID with the description embedding. Here, I modified the code to print the first 2 documents. So here we can see the 2 documents that are printed to the console have been modified with a description embedding field containing an array with 384 vector description. Now that the transactions have been properly processed, we will now compare the results of a MongoDB vector search and a manual dot product search. Here's the result of running the MongoDB vector search with the past user ID and the query brunch. So, I asked for the 5 most similar documents, but I only received 3 documents, one of which is a duplicate with the same exact ID, which is one of the reasons why I decided to use a set so that I would not receive any duplicate elements. But still, I only received 3, and I needed 5. These are some of the reasons why I decided to implement my dot product similarity search manually. So I'm going to walk through the steps of manually implementing the dot product similarity search, and we can talk about the benefits and downfalls of manual implementation. MyQuery transactions is the manually implemented dot product similarity search function. The dot product list variable, which will add an array of each document, and the dot product result is first declared. Next, an embedding of the parameterized query is generated and assigned to the embedding variable. Then, the result of all transactions matching the parameterized user ID with an existing description embedding field is iterated through. In each iteration, the desired fields to be displayed are saved to the save dictionary. Next, an array is created with the save dictionary in its first index, and the dot product of the description embedding and the query embedding using the numpy dot function. This array is then appended to the dot product list. This ends the for loop iteration. After termination of the for loop, the dot product list is sorted in descending order by its second index using the sorted function. Since index counting starts at 0 in Python, the second index is 1. The first index, containing only the save dictionary, is assigned to the result variable. The more similar two vectorized embeddings are, the larger the dot product. This is why the list is sorted in descending order of the index containing the dot product of the two embeddings. Lastly, the 5 most similar results will be saved to the t_results.json file. Let's run the myQuery transactions function and see how it works. Here, just like the vector search, we retrieve the work luncheon transaction first, which is the most similar transaction to the query brunch. Next is our facial transaction, and then new brake lights, home gas bill, and gas tank refill. Here we can see the function returns transactions in the order most similar to the query. Now we will jump into the dot product search manual implementation, pros and cons. Pros: greater control of the similarity search process. With manual implementation, I was able to retrieve the 5 most similar transactions to the query. I was unable to do that with the MongoDB vector search. 2. Time complexity control. The implementation shown earlier results in a big O of n for the outer for loop. However, this can be reduced to big O log of n with a divide and conquer approach. 3. Increased result quality. The manual dot product search returned exactly the number of specified transactions in the order most similar to the query. Cons of manual implementation. 1. Without the vector search, there is no MongoDB search indexing, which is something to consider. 2. There's a less direct pipeline process. MongoDB offers a direct pipeline process, while manual implementation is just a series of functions. Lastly, and most consequently, re-implementation is necessary in manual implementation for different types of similarity searches. Conversely, only one line in the vector search declaration needs to be modified to change the similarity search in MongoDB. I hope I have enlightened you on how to conduct a RAG pipeline using both MongoDB's vector search and a manual dot product implementation. Thank you for joining me in the Budgetier Application RAG pipeline breakdown. Have a great day!